All right, let's get right into it. Today, we're basically going to be molecular detectives, solving a biological mystery that happens on an atomic scale. Our case? Cracking how a tiny enzyme does its job with just unbelievable precision. So welcome to our molecular detective story, how chymotrypsin works. Okay, so meet our main character. This is chymotrypsin. It's a total workhorse enzyme in your digestive system. And you can think of it like a molecular machine, right? A pair of super specialized scissors. Its whole job is to snip apart the proteins you eat into smaller bits your body can actually use. But here's the real mystery. Proteins aren't simple. They're these long, complicated chains. So how in the world does this tiny pair of scissors know exactly where to cut? I mean, it doesn't just snip at random. It is incredibly specific. So how does it know where and how to make that perfect cut? That is the case we're about to crack. And that brings us right to the first part of our investigation, a molecular mystery. So, chymotrypsin's mission, should it choose to accept it, is to precisely break these specific links in proteins. They're called peptide bonds. Now, to figure out how it works its magic, scientists couldn't just, watch it happen. It's way too fast and way too small. Instead, they had to act like detectives, looking for clues and piecing together all the evidence. So our investigation kicks off with our first major piece of evidence. Let's call this one Clue 1, the initial burst. When scientists started measuring how fast this reaction happens, they found something weird. Instead of just a steady, predictable speed, they saw this pattern. First, there was this super fast, like almost instant, burst of product being made. But then, right after that, the reaction just settled down into a much slower, steadier pace. This was a huge, huge clue. So why two different speeds? What's going on? Well, this pattern was basically the enzyme spilling its secrets. It told us that the whole reaction isn't just one single thing. Nope, it actually happens in two totally separate phases. There's a lightning-fast first step, which creates that initial burst, and that's followed by a much slower second step, which is what sets the overall pace. And here's the key to that fast step. The enzyme actually forms a temporary physical bond with the chunk of the protein it's cutting. It's called an acyl-enzyme intermediate. And in this state, the first half of the protein has been snipped off and released, that's our burst, but the second half is still physically stuck to the enzyme. The slow part of the reaction, that's just the process of cutting that second piece free. And just like that, clue number 1 is solved. Okay, but knowing there are two steps isn't the whole story. We need to know who the key players are in the active site. So let's move on to our next piece of evidence. Clue 2, the perfect conditions. Just like any good detective, chymotrypsin is a little bit picky. It works best under very specific conditions. Just look at this graph. It shows the enzyme's activity at different pH levels. You can see it's a perfect bell curve. It's pretty lazy at low pH, not great at high pH, but it has this perfect Goldilocks zone right around a pH of 8, where it's an absolute superstar. This sensitivity, it's another huge clue. So why would pH matter so much? Well, because changing the pH messes with the little charges on specific amino acids, the building blocks of the enzyme itself. This pH profile was like leaving a fingerprint at the crime scene. It allows scientists to pinpoint the key amino acid suspects in the active site that were doing all the heavy lifting. The investigation really narrowed in on two main culprits, which you can see right here. If the pH drops below 7, a key player called histidine 57 gets an extra proton stuck to it. And when that happens, it can't do its job of kickstarting the whole reaction, so activity just tanks. Now, on the flip side, if the pH gets too high, above 8.5, a different amino acid, isoleucine 16, loses its proton. This breaks a critical connection that holds the enzyme in the right shape, basically warping the active site so it can't work anymore. Two key players identified. Okay, we've got our clues, we know it's a two-step process, and we know who the key suspects are. So now it's time to put it all together. The mechanism revealed. So at the absolute heart of the chymotrypsin mystery is this incredible molecular A-team, the catalytic triad. It's this super precisely arranged group of 3 amino acids, serine 195, histidine 57, and aspartate 102. And they are just neighbors. They are locked in this beautiful network, working together like a coordinated chemical ballet to break that peptide bond. So here's the game plan, broken down into 2 main phases. First up is the acylation phase. This is where the triad attacks the peptide bond, breaks it, and forms that acyl-enzyme intermediate we talked about.
boom, the first half of the protein is released. Then comes the deacylation phase. A water molecule swoops in, breaks the bond to the enzyme, and releases that second half, which totally resets the enzyme so it's ready for another round.
Let's zoom right in on that first critical moment. With help from its teammates, serine 195 becomes this powerful attacker, and it slams into the carbon of the peptide bond. This creates a really unstable, very temporary structure called a tetrahedral intermediate. It's this high-energy, fleeting thing, and the enzyme needs a clever way to deal with it. And of course it has one. It's another awesome feature called the oxyanion hole. This is a special little pocket right there in the active site, and it's perfectly shaped to stabilize that unstable, negatively charged thing from the last step. It's like a built-in safety net, holding it steady and making the whole reaction way easier to pull off. So with that intermediate held perfectly in place, it collapses almost immediately. And this is the moment of truth. The whole structure reforms, and in doing so, it forces that peptide bond to just break. The first piece of the protein is now free, it just floats away, and what's left is our acyl-enzyme intermediate, with the other half of the protein still stuck to the enzyme. Phase 1, complete.
All right, on to phase 2, the big reset. A totally unsuspecting water molecule wanders into the active site, and our old friend, histidine 57, grabs it and activates it, turning it into a powerful attacker. This newly activated water molecule then does the exact same kind of attack on the intermediate that the serine did on the original protein. It's all getting ready to break that final bond.
I mean, how incredible is that? The chymotrypsin mechanism is just a beautiful, beautiful piece of molecular engineering. But this kind of strategy, it's not unique. It's really just one chapter in a much bigger story, the story of nature's master machines. This whole combination of a catalytic triad and an oxyanion hole, it's an absolutely brilliant solution. But it's not the only way to get things done. Enzymes have evolved this huge bag of tricks, just countless different strategies to do their specific jobs with mind-boggling efficiency. For example, take a look at hexokinase. On the left, you see it's just kind of hanging out in this open, inactive state. But watch what happens when its target, a glucose molecule, comes along. The entire enzyme clamps down on it, completely changing its shape, like it's giving the glucose a big hug. This dramatic transformation, it's a totally different strategy called induced fit. So induced fit is this idea that the very act of the substrate binding makes the enzyme change its shape into a more powerful, more active form. It's less like a rigid lock and key and more like a glove that only forms a perfect fist once the ball is actually inside. The enzyme uses the energy of binding to get itself ready for action. You know, from chymotrypsin's super precise chemical teamwork to hexokinase's dramatic shape-shifting, we're seeing nature's incredible ingenuity on full display. And chymotrypsin is just one of thousands of enzymes, each one a master of its own craft. Which really just leaves you with a final thought, doesn't it? What other elegant solutions has nature engineered at the atomic scale?